Welcome back to the reactor deep dive. Today we are going really fundamental looking at the heat and how it moves, especially how it moves when it begins generated from inside a material itself. Well, two pretty cool ways, electrical wires and then the nuclear fuel elements. Right. And our mission is how the temperature actually behaves. It changes in this system when you have heat actively being produced inside of them.
Exactly. And the material you shared, it actually lies out a really nice foundation. Core principles of analyzing energy, focusing specially on heat. And then it applies those principles to these two kind of distinct but equally important scenarios. A wire carrying an electric current, a spherical fuel elements. So by looking, we can really get grasp of the underlying physics driving everything.
Yeah. The principle governing something as simple as a wire getting hot and sometimes as complex as a nuclear reactor.
Right, right.
Like, have you ever thought about why thin wires get hot when you plug something in? Or how the incredible heat in a nuclear reactor is controlled so precisely?
Probably not on daily basis, but
It's really these kind of questions that showcase just how wide ranging the implications of heat transfer are. So, alright, let's get into it.
okay. So when we think about how to analyze heat flow in this situation, the first thing your sources introduce is the concept of shell energy balance. That's okay. Now imagine taking a tiny slice of the material. We are looking at whether it's wire or fuel elements. It's called shell, okay? It's called shell, okay? And the shell energy balance basically accounting for all the energy flowing into this tiny shell and all the energy flowing out. And this is key. Any energy being generated within that small volume itself. It's like keeping track of energy budget for this microscopic part of system.
So, we are not looking at the whole wire or the fuel elements all at once. We are focusing on this tiny piece.
Exactly. And to make this balance work, to actually figure out the temperature, how it distributed, we need all called boundary conditions all.
Right, boundaries, yes.
Your sources outline several important types. One sample just knowing the temperature and specific surfaces. Like we might know the outer surface of the wire is held at certain temperature. Maybe because of touching something that carries heat away.
Like if it was submerged, like a cooling liquid or something. Right, that makes sense.
And the heat flux also has to be continuous, meaning the rate at which heat is leaving one material must be the same as the rate it's entering the other.
It's like saying heat doesn't get stuck at the interface. It has to flow smoothly.
Exactly. Finally, we have the Newton's law of cooling. This is one describes how solid surface exchanges heat with moving fluid like air or water. Basically, the heat flows between two is proportional to the temperature difference between them. And the heat transfer coefficient tell us how efficiently that exchange these boundary conditions. Without them, we can't solve the problems.
Okay, so we got the idea of tracking energy in a tiny part of the system and then the rules that apply at the edges. Now let's dive into the example, the electrical wire.
Right. So your material looking at wire with circular cross section and well, an electric current going through it. The key here is that unless it's superconductor, the wire resists the flow of electricity a little bit. And the resistance causes some of that electrical energy to turn into heat.
Like, have you ever thought about Why thin wires get hot when you plug something in, or how the incredible heat in a nuclear reactor is controlled so precisely.
Absolutely. Think of everyday appliances with the heating elements: toaster, hair dryer, even old school light bulbs. And to make this balance work, to actually figure out the temperature, how it distributed, we need all what are called boundary conditions all.
So it's heating itself up from the inside as the current passes though. It's not just getting hot from the some outside source.
Exactly, and the rate at which this happens, how much heat is generated per unit volume, depends on two things: the current density, which is low packed the current is in the wire cross section area. These things of like how crowded the electrons are, and the electrical conductivity of the material, how easily those electrons can move.
So a thicker wire means less crowded electrons and a material that conducts electricity well should generate less heat. Right? Like a real wire.
Consider a situation where the surface of the wire is kept at a constant temperature, and by applying shell energy balance, the law called Fourier's law, we can actually figure out how the temperature changes across the wire radius. It's called the temperature profile, and how the heat flow. The heat flux changes too. The key finding here is that the highest temperature is right at the center of the wire.
So this isn't just a theoretical exercise. We see this all this time in a real world, right?
Precisely, the further you go, the more resistance the heat faces. Now, your thoughts look at more realistic scenario where the wire isn't perfectly cool. It's losing heat to the surrounding air.
Well, you mentioned toasters and hair dryers. I guess the thickness of the wire or how much power it uses. Be carefully calculated to get the right amount of heat but not melt or burn out.
Absolutely. Think of everyday appliances with the heating elements: toaster, hair dryer, even old school light bulbs.
So engineers can actually use these equations to design a wire for a specific application. Make sure it can handle the current and not get burned out. That's interesting. I would have thought it would be more or less uniform throughout the fuel. No heat mysteriously building up or disappearing at the boundaries. Makes sense. It's generating heat all throughout, and that heat has to travel outside to the surface to skip. The center is the furthest point. So it's not just about how much heat is generated, but also the properties of the material and how they conduct heat. Really makes you. Absolutely. And thank you for joining the reactor deep dive.
Right. So today we are going to take a deep dive into a spherical fuel elements and how heat moves through spherical nuclear fuel elements. Have this dense little sphere that just cracking out a tremendous amount of energy. You know, it's like a tiny little powerhouse. What we want to do today is really understandable. How the heat actually travels from the inside of the fuel to the outside of the world. So just jump into the right in and to kind of set stage here. We are talking about the ball of fissionable material. We are going to call the radius of the ball material RF. Now the fissionable material, you know, it's not just a sitting out there in the open. It's encased in a layer of aluminum that we call the cladding. And the cladding has the radius that extend out RC and outer edge of the cladding is kept at the steady state. Now the temperature is constant with the theta and phi. Temperature is varying with the radius, that is T of R. The heat generation in the fuel element it's more intense. The center of the fuel element and it moves outwards towards the cladding. It decreases. Now the coordinate system of this question is the spherical coordinates. Coordinate system is the spherical. Origin is at the center. Origin at center. The temperature variation is the variation with respect to R and the constant with theta and phi. So the temperature constant with theta and phi. Temperature varying with radius R. Temperature varying with radius R. So the temperature is the function of R. Okay. Now the spherical shell of thickness delta R. Spherical shell of thickness delta R. Inner radius is the R and the outer radius is the R plus delta R. So now I will draw the figure. So this is the sphere which is the radius R and the outer radius is the R plus delta R. The thickness is their delta R. Thickness is the difference between the inner radius and the outer radius. Now we will discuss the shell energy balance. So for the shell energy balance, shell energy balance now cell energy balance is the rate of energy in by convective transport minus rate of energy out by convective transport. But TF is equal to minus Sn naught by Kf r square to the power 6 divided by BRF r to the power 4 by 20 plus C2F. So the boundary condition 3 will be the at R is equal to the RF. Boundary condition 4 will be the at R is equal to RC. Now that we can get the directly equation from these boundary conditions by substituting the boundary condition in this equation. So the boundary condition TF is equal to Sn naught RF whole square divided by 6KF 1 minus RF whole square plus 3 by 10 B 1 minus R by RF whole to the power 4 plus Sn naught divided by 3Kc RF whole to the power square 1 plus 3 by 5B 1 minus RF divided by RC plus T naught. Now by substituting this equation we got the TF equation. Now we will write the TC at the boundary condition. TC will be the TC is the temperature profile at the TC. Sn naught divided by 3Kc RF whole to the power square 1 plus 3 by 5 B RF divided by R minus RF divided by RC plus T naught. We have got these two equations from the boundary condition at R is equal to RF and R is equal to RC. Now these are the final equation. We have got the TF and TC. So previously we have discussing the boundary conditions. First one is the temperature may be specified at a surface at R is equal to the RC, TC is equal to the T naught. Second one is the interface of the continuity at R is equal to the RF. R is equal to the RF, TF is equal to the TC. So from this we can write the TF is equal to the Sn naught minus divided by Kf r square divided by 6 divided by b divided by rf whole to the power square r to the power 4 divided by 20 plus c1f, sorry c2f. Now the second equation Tc is equal to the Sn naught divided by Kc 1 by 3 plus b by 5 Rf to the power 3 divided by R C2F. So the third boundary condition will be the boundary condition 3. The third boundary condition at R is equal to the Rf.